Right, so the last time we looked at buffers, we were actually looking at how you can determine the pH of a buffer, knowing how it was put together. However, really what we want to do is to be able to make a buffer where we know what pH we want. So let's say we had a system that we had to keep at a pH of 5.00, and we had sodium ethanoate and ethanoic acid available to us. And those were the ethanoic acid we know to be 1.00 moles per litre. What we need to be able to do is to say how we would make this buffer. There's a couple of assumptions we're going to make here. We're dissolving a solid into a solution. We're going to assume that the volume doesn't change. Alright, so that's one of our things. We're going to say that there is no change in volume. Now, technically, when you're adding a mass to a solution, adding a solute to a solution, it is going to change the volume a little bit. But let's assume that it's not going to. Otherwise, it gets a bit tricky to do this. Also, to be honest, in the limits of accuracy we're looking at, it won't make a difference. So there's some things that we're going to look for in our question. One is that we've got our concentration. We've got our concentration of our acid. I'm sorry, I've forgotten the question to say how much we've used there. It's meant to say 100 mils. I forgot to put it in there. Sorry about that, I forgot to put that when I was writing it up. So you've got 100 mils of 1 mol per litre ethanoic acid. Alright, we also know about the ethanoic acid, we know it's Ka from its pKa. So we 10 to the negative 4.76. We know a little bit about the conjugate base as well. We've got a molar mass, but that's about all we know. So it's a bit hard to know where to start. Well, you guys know me well enough now to know where I'm going to start. I'm going to start with an equation. So what I'm going to do here, even though it's a buffer, which means it's got an acid and its conjugate base present in similar concentrations, I'm going to start with the acid dissociation equation because I've got a Ka, so I might as well do the acid equation. So I'm going to do that here. CH3COOH, so my ethanoic acid, plus water dissociating, because it's a solution that I'm starting with, so I can say water. CH3CO minus plus H3O plus. Now the ethanoate ion there is the sodium ethanoate. Okay, so that's where that's being provided. The ethanoic acid is the solution that we're putting it into. So the next thing I'm going to do is I'm not going to do my Ka just yet. I'm going to write down what I know. So under my ethanoic acid, I know that it's got a concentration of 1.00 moles per litre. I know, I'm sorry about forgetting that before, I've got 100 mils of it. Or 0.100 litres, if I want to get it into the correct unit. I know that I've got this in the form of sodium ethanoate. This is going to be one of my unknowns now, but I do know that the molar mass of the salt that comes from is 82 grams per mole. So even though the sodium's not shown in this equation, I've got to remember that it is there. When I add it as a salt, the sodium is present. Sorry, the other thing I've forgotten over here is that I've got a Ka for it, because that can be really useful. And I actually know a fair bit about my hydroniums in this case. In this case, I'm asked to make something with a desired pH of 5.0. Well, I know that the relationship between pH and hydronium, I know this relationship, so I can do that pretty quickly too. It's going to be pH is negative log of the hydronium ion concentration, so therefore hydronium is 10 to the negative pH. Well, that's pretty easy for me to write up. That'll be 10 to the negative 5 moles per litre. So that's not particularly well, so I'll just fix it up. So 10 to the negative 5 moles per litre. So I've actually got a bit of information. Now I'm going to write my Ka expression. Alright, so I'm going to write my Ka expression for this and see what I'm missing. Ka equals the ethanoate ion concentration times the hydronium ion concentration. And my big warning to you here is these two values are not the same. Remember, in a buffer, these two numbers are not the same. This is a buffer, so they're not the same. All of this divided by my ethanoic acid concentration. Now because ethanoic acid is a weak acid, this 1 mole per litre will stay as 1 mole per litre. So I can actually substitute some numbers and algebra in there. I don't know this one. It's my unknown. So I'm going to call it x, because I like working with x for algebra. Ka I've got. This is 1.00, and this is 10 to the negative 5. So I've actually only got one unknown in my whole equation. So I can redo this equation to make x, or ethanoate concentration, the subject. So let's do that. So I'm going to call it x just because I'm running out of board space. I'm going to multiply that one through there. So it'll be 1.00 times 10 to the negative 4.76. And then divide 10 to the negative 5 out of both sides. And I get that little expression there. Sounds pretty ugly and very mathsy. Hopefully you can see it's basically just a ratio between those two though. Okay? So for those who are over it pretty quickly, you'll see what we're going to get there. Anyway, 10 power of negative 4.76 divided by 10 power of negative 5 is 1.74 to 3 SF. Now this is a concentration, so we'll go moles per litre. So it's pretty high. That's not a surprise because we started with 1 mole per litre of ethanoic acid. So those two numbers should be in the same sort of ballpark. If you've got something down at say 10 to the negative 3 or something like that, then you know this is wrong because it's so far away from that. A buffer needs to be made of a base and its conjugate acid, or an acid and its conjugate base in relatively similar concentrations. Okay, so that tells me what concentration to use, but that's not what I've got in the question. I've got a solid being dissolved in a solution. So what I need to do there is go, well, how many moles is that? How many moles is that? So this is where my volume becomes important. So I'm putting this into 100 mils. So I can also put that over here. So what that means is that I can actually take this concentration, which I now know is here. So I now know this is 1.74 moles per litre, to find an amount or number of moles. So my next thing is to use N equals little m over big M, or MR. Because I know this value, I need to have this one, so I need to find my number of moles. But in the data I've got here, I'm going to need to use concentration, which we've got 1.74, and my volume is the same as my volume of my acid because I've dissolved it into the acid. The acid was the solvent. So I can go, the number of moles of ethanoate ions, again, I'm not worried about the sodium yet, that'll come in a moment, it's not shown here, is the concentration 1.74 times 100 over 1,000. Over 1,000 because I need to get my mils into litres. So it's quite easy, 0.174 moles of that ion. Now my next thing to check is how many of those ions are in sodium ethanoate. Alright, because if it wasn't a 1-to-1 ratio, then I need to consider that in working out the mass. Alright? Luckily though, sodium ethanoate has only got one of them in it, so it's okay. Alright? If there were two of them, then I'd need to halve this value. So if it was say calcium ethanoate, which would have 2 ethanoate ions, then this value would have to be halved, because there's half as many moles of the original stuff as there are of the ethanoate. Okay? If you need to know some more about that, ask me later on. Alright, so therefore the number of moles of sodium ethanoate, there's only one of them, is also equal to 0.174 moles, because there's only one ethanoate in the salt. Then I can go back up here and rearrange this, where mass is equal to the number of moles times the molar mass. And we're given the molar mass as 82. So we just go 0.174. Actually, ideally the number wouldn't have been rounded off yet, so 0.173780 keeps going from there, times 82.0. And we get 14.24, so 14.2 grams. So you have to put quite a lot in there, just into 100 mils to make this buffer, because the concentration of rethanoic acid is so high. Alright, so that's showing how to make one. Just to sum up, when you're asked to make a buffer, you're told the pH. The pH tells you your hydronium ion concentration. You should also be given a Ka or a pKa. That's going to be really important because that gives you those two there. One of these two will almost certainly be a solution of a known concentration. So you can put that number in, and in this case it was 1.00 because I wanted to make it easy for myself. So the concentration of your solvent can go in, whichever one it is. Then the other one is normally a salt being dissolved into that. So it's normally a solute, and you just have to assume that there's no change in volume to be able to do the calculation.